Hello and welcome. This is Professor Richard Holowczak, and this is a presentation on file formats for data engineering, data analytics, and data science. I was inspired to create this presentation by a post from Aida NGOM, comparison of different file formats in big data. So many of the ideas in this presentation are due to Aida's article, which I have linked here and I'll put down in the description. So what are we going to talk about today? First, why are there so many different file formats? We're then going to talk about columns, data types, and schemas. We'll talk about how data records are oriented within a file. We'll talk about whether or not files can be split and why that's important. We'll talk about some different use cases for data files, and we'll discuss a whole bunch of different file formats. And finally, we'll end with a summary. So first up, why are there so many file formats? Well, for as long as computer storage has existed, data has been stored in files. The basic way this works is we have a file that's sitting here on disk, and that file is loaded up into random access memory, into our RAM. And once that file is loaded into RAM, our CPU can compute on that file, it can process that file, it can even create a new file, which then from RAM will be written back to disk. And so disk is where we have this non-volatile storage, and when we write files to disk, they need to be written in a particular storage format. Files are used to both store data as well as exchange data. So if we have a business partner or we have a research partner or a teammate, we need to be able to exchange data with them in an accurate and convenient way. There are going to be many trade-offs. File formats can be simple and they can be very, very complex. The data themselves can be stored in a binary format versus a text format that humans can read. There can be a variety of use cases, such as an analytical use case where we're just analyzing data, or a transactional use case maybe where we're writing and updating the data. Our data can contain a schema, which I'm going to explain in a little bit, that defines the columns and how the data is organized, or the file could be schemaless, and just a sort of a blob of data that we have to interpret ourselves. And we can talk about how the data is organized internally. That also ties into the simplicity versus complexity. There are two general methods used to represent data. The first is simply text, and that's just in plain letters and numbers and characters that we can read as a human. For example, a comma-separated values file, sometimes abbreviated CSV, or a tab-separated values file, are text. Anyone can open up that file with a text editor and you can read the data that is there and you can make some sense out of it. Another way to store the data is in a binary file. So the data is stored in some binary encoded format. If you or I looked at a binary file, we wouldn't be able to tell what's in there. And an example would be like a JPEG image file. Now let's talk about columns, data types, and schemas. When a data file is read, the programming language, like Python or Java, needs to assign data types to each of the columns or fields. For example, on the side here, I have an example of a comma-separated values file. We might consider the customer ID to be some kind of a character string because it has some letters in there. Last name and first name and city and state are also character strings. But what if we had a zip code in there? Maybe that zip code could be a character string or a number. We don't know. So we need to be able to assign a particular data type to each column of our data. And the typical data types we use are some type of a string, which can contain letters and numbers, an integer number, a floating point number, a Boolean, which might be true or false, or a 1 or a 0, and maybe a date or a time or some combination of date and time. The arrangement of the column names and their data types is called a schema. And if you've taken a database management systems course, you probably recognize this as the collection of tables with their columns and their data types. So we borrow that same idea. It's the arrangement of the data, what we're going to call each column, and what the data type might be. Some of the file formats include some or all of the schema along with the data. For example, in my CSV file here, we get the names of each of the columns, but we don't see what the data types are. There's another file format we'll talk about called a Parquet file. and that embeds both the column names and their data types within the file along with the data. So this helps when we need to read that data. We already are given what the names of the columns and their data types will be. Next, we're going to talk about record orientation. And the typical way data is oriented in most text files is in row orientation. That is, each record of the data is stored on its own row. So if we look at this example in the upper right corner, we see customer 101 is Joe Smith in Hanover, New Jersey, and that is one complete data record. Then we go on to the next row. Customer 102, Ed Green in Lodi, New York, and so on. So each record of data is on its own row. Sometimes we'll call this an observation, or a record, or a row, and this is generally good for transaction processing, because when we add a new customer, for example, we can simply zip down to the end of our file and we can add a new record without any problem whatsoever. The disadvantage of this approach is if we want to, say, count up all of our customers who live in New Jersey, we have to go through all of the data. We have to read all of the rows until we can get to where the state is here, NJ, and then we can count them up. So there's a lot of extra data that we have to go through just to get to that. So row orientation is generally good for transaction processing, but not so good when we want to analyze the data. By contrast, column orientation stores each column of data together. And here's an example. Here we've stored all the customer IDs together. Then we've stored all the last names, the first names, the cities, and the states. You see how each of these is clustered together. Now, the great thing about this is, if we want to analyze the data, again, like our hypothetical query, how many customers live in New Jersey, all we have to do is just grab this one area of the data file, and we can very easily count up the number of New Jerseys that show up here. We basically can ignore all of the other columns. This is also pretty good for compression. If all of the similar data is together in the same column, we can very easily compress this and save some space. Column orientation is great for analytical purposes because we can pick and choose a couple of columns at a time. However, they're not very good for transaction processing. Why? Because to add a record, we have to go and visit each of these column blocks, and that's going to take a little bit of time. We can't just simply zip to the end of a file and add a record and be done. We have to actually go in and update each of these little column areas. Next, I want to talk about file splitting. Distributed file systems like the Hadoop distributed file system split files into multiple blocks. Those blocks are going to be stored on different data nodes, and processing tasks can then operate on these multiple blocks in parallel. So here's an example. We start with a big file, and Hadoop will actually break that file up into 4 blocks, let's say, and then those blocks are spread across a series of nodes. So not only does this help speed up processing, but it also gives us some resiliency. If node E were to fail, we still have copies of those blocks on other nodes. When we want to process this file, we can work on, say, node B to work on block 1, node A to work on block 2, node C to work on block 3, and node D to work on block 4. And this processing work can be done in parallel, what we sometimes call parallel processing. This is great for analytical workloads and great for data processing. Some file formats can be easily split. For example, CSV, because it's row orientation, we can split some of the rows into a block and put those out on a node. JSON documents in a particular what's called row orientation, Parquet files, Avro, and ORC files have all been designed to be easily split. Now let's talk about some use cases. I already mentioned this a little bit, but one of the very common use cases is for transaction processing. This is sometimes called online transaction processing, or OLTP. New records are written at the end of the file, and queries for specific records are based on an index, and most of the columns are returned. For example, please tell me all about customer 103. We can immediately return exactly one record. Updates are going to happen in place. So we need a file format that will allow us to go into a file and update a little bit of data in place. So that's a very specific use case. Analytical processing is a little different. A collection of records is basically written one time to disk, and then we do a whole bunch of queries. Something like a data lake or a data warehouse is set up for analytical processing, or OLAP, online analytical processing. Queries typically go across most of the records, but only for select columns. So it's kind of the opposite of the transaction processing use case. And in general, updates are not done, so we don't have to worry about rewriting parts of the file. Another use case is when we want to transfer data. For example, we might have data in our database that we want to share with a business partner. We might create a purchase order, for example, and the data about our purchase order needs to be transmitted over to our vendor. Here, the importance is on schema mapping. That means the collection of columns and data types in our database need to line up with the columns and data types of our business partner's database. Generally, data size is not much of an issue, and how the data is oriented is not really much of an issue. It's more about, is there a convenient way that we can map our schema onto our business partner's schema so we can get that data transferred between us. The last use case is the streaming use case. Here, we have streaming data sources like web clicks every time a customer clicks on our website, or an app gesture every time someone selects a button or swipes on our app. Internet of Things sensors like smart thermostats or Ring doorbells. Security logs when someone tries to connect to a system within our company and that generates a security log. These are all streaming sources of data. These are data that come in on a continuous basis. Each message from one of these sources contains a data record, and in general, we're going to append those to the end of the file. So how our file is organized really is very similar to what we need for the transaction processing use case. We just have a stream of messages coming in, and we need to rapidly append those to a file while still making the data accessible. So these are sort of 4 different use cases that we need to think about when we're choosing a file type to work with. So now let's dig in with our actual file types. The first is the most common, and that's what we call comma-separated value files, CSV. I've given you the specification here. I'll put all the links down in the description. This is a text file format, but data types are not stored within the file and they're not enforced. CSV files have row-oriented storage, like we talked about previously, and the typical use case would be transaction processing or storage, exchange, and also streaming. If we want to compress this data, we can use some external compression. Usually that's something like gzip or bzip or something like that. And again, it's useful for batch and stream processing because it's very easy to add new records to the end of the file. Typically, when we write a record in a CSV file, the end of the record is signified by either a carriage return or a line feed or both characters. And sometimes when we move files, CSV files, between systems, that carriage return or the line feed can actually be stripped off or translated in some way. But there needs to be some way to indicate, hey, we're at the end of this record and now we're going to start up with the next record in our file. Python has libraries specifically for CSV files, but most of the time when we read a CSV file, we want to read it into a pandas data frame. And to do that, we can use the read CSV function. There's various options for read CSV. There's, I think, actually more than 20 or 25 options. There are various options that allow us to specify what that header row is, what the separator might be, whether or not we have compression, and so on. So I've just given you a couple of common options to try here. Usually the header is in the first row, what we call row 0, but if it isn't, you can specify the header. If we get to a record in the file and Python is unable to parse that for some reason. It's unable to find where the commas are or something is wrong. We can actually tell it, okay, just skip those lines. If there are problems parsing a file, we can ask the read CSV to just continue reading anyway, or we can say, you know what, when you get an error, stop and throw up that error. That's what the error bad lines is going to control. If we have compressed files, we can specify the compression with that option. If we have a very large CSV file and we're just doing a little bit of exploratory data analysis, we're not really sure if we're going to use this data, we can actually read in a portion of the file with the nrows option. And as I mentioned, the delimiter, the default is a comma, but we could also have a tab delimited file. That's with the /t. Or we could have semicolon delimited, or actually anything else like the pipe symbol and so on. So you can go through the documentation for read CSV. There are many, many more options. The basic way we do this is we import pandas and we alias it with PD. We specify our file name, and then we simply call PD read CSV with the name of our file and whatever separator or other options we might want to include. Once that's parsed successfully, it will be stored in a data frame, and the typical name we give it is DF, and all of our data will be read from disk and into memory. And once it's in the data frame, we can go ahead and work with it. The next very common type of file is called a JSON file, or sometimes called a JSON document. JSON stands for JavaScript Object Notation. It's a text document with a collection of name-value pairs. You can see the link to the specification. This is also a text file format. Data types are not stored within the file and they're not enforced. Typically, JSON files are using row-oriented storage. However, that's not always the case, and I'll show some options in the next slide of how we can deal with these different styles of JSON files. The typical use case might be document storage with semi-structured data and also for streaming. For example, if we have a series of reviews on our products or our restaurant, there will be some parts of that file that are structured, like how many stars was it given, how many upvotes it received, as well as some free-form text that has the review text itself. So JSON documents are able to store this sort of mix of structured and semi-structured data. For reading JSON files, Python has a JSON library by itself, but again, most of the times we want to read this data directly into a pandas data frame, and we can do that with the read JSON function. Just like in read CSV, there's a whole bunch of options that you can specify in order to control how the file is read. The orient records option is used when the JSON file has a key index, so some type of a key and a value will be the actual document itself. The orient equals index is used when the JSON file has a numeric index for each JSON object. The other important option is lines. If lines is set to true, then the JSON file has basically one JSON object per line in the file. If this is set to false, it assumes that it's following the full JSON structure that begins with a curly brace and ends with a curly brace. To read a JSON file is pretty straightforward. Again, we're going to import our pandas library, set our file name. We can simply call the read JSON as the file name and specify whether lines are true or false and what the orientation might be. And then again, that's going to be parsed and set to a data frame. The next file format I'm going to talk about are XML files. XML stands for Extensible Markup Language, and you can see the link to the specification here. XML files have document-oriented storage, meaning the entire file is basically an XML document. It's a text file format with explicit opening and closing tags around the data. So you can see here, for example, we have a product list that is a collection of products. And for each product, we have an opening tag and a closing tag with that little /product. Down here, our product list ends. So this basic format gives us an XML document. The schema specification is typically stored externally in what's called an XML schema. Generally, XML files are not splittable since the entire document ends with a closing tag. The typical use case for XML files is for data exchange. For example, if I want to exchange this product list with one of my business partners, XML would be the way to do that. XML is used quite a bit in the enterprise and sort of business-to-business world. Python has an XML library called LXML with many advanced capabilities to read nested XML documents where we have one document within another. For relatively simple XML files, we can read the file into Pandas data frame with the read XML function. And this is very similar to what we saw with read CSV and read JSON. The one important option here is what's called the XPath option, and this is used when we want to parse only a part of the XML file. When we use this option, the */*, the asterisk means we want to parse all of the different parts of the XML file. The next file type I want to talk about are pickle files. Pickle files can store and retrieve any Python data structure, including data frames. So if you have a list or a dictionary or a data frame, anything can be stored in a pickle file, what they call pickling. The specification is shown here at this URL. It is a binary file format, and data types are stored together with the actual data. However, pickle files are not splittable because they are really just a representation of that data structure in memory. You can compress pickle files, for example, with gzip. Of course, Pandas has a read pickle function, and it assumes the pickle file was serialized from a data frame, meaning it had to have come from a data frame, and then you can load it back into a data frame. The typical file extension is .pkl, and one of the options that it has is whether or not the file is compressed, and it actually has this nifty infer option, which basically will automatically determine whether or not the pickle file was compressed. So it's a fairly straightforward PD read pickle and your file name, and then you can infer the compression, and that will unpickle your pickle file into a data frame. The next file type to look at is Avro. Avro contains a schema along with binary data, and you can see the specification at avroapache.org. The schema is included in the file as a JSON document. So you sort of have this header at the beginning of the document, which is JSON, at the beginning of the file, which is a JSON document that describes all of the columns and their data types. And then that's followed by the data in a binary format. Avro files are row-oriented storage, and the file actually contains markers where those rows can be split up. Data is compressed internally using what's called a codec, an encoder-decoder. Typically that codec is either bzip2 or zlib or something like that. So internally within the file, the data is already compressed. The typical use case for Avro files are data exchange in the Hadoop ecosystem and for streaming. So you can imagine a set of streaming messages where the very first thing you get is the schema and the data types as a JSON document, and that's followed by these binary encoded data records or rows that get sent afterwards. Over the years, there are 3 different Python libraries that have been created to work with Avro files. There's Avro Python 3, there's FastAvro, and PandAvro. Let's take a look at those. So dealing with Avro files is a little bit more tricky. This is the Avro Python 3 implementation. You import Avro, you have to import JSON and pandas. Basically, you open up your Avro file, which is represented as the file name here. You create a data file reader, which is something that comes with the Avro module. And then you copy out the metadata, which again is that JSON document that has the column names and the data types. You can then express that schema in a variable here called schema from file using the JSON loads function that we get from the JSON library. And then you can actually get the data. So my data here would result from iterating over all of the records that you find in the reader. And then of course you close out that reader. By the time this is all done, my data is holding all of our data records. and then we can use this function called fromRecords and then assign it to a data frame. So dealing with Avro files with Avro Python 3 is a little bit more complex. Using FastAvro is fairly similar. In FastAvro, these functions are implemented in the C++ programming language, so they're a little bit faster. But as you can see, the order of operations is quite similar, and basically the results end up in a data frame as well. So this is just a little bit of a faster implementation using FastAvro. And then finally, PandAvro hides a lot of the complexity. PandAvro has a whole bunch of dependencies that you have to install. You basically import PandAvro and pandas, and then you can use the fromAvro function, which again basically implements all of those details of extracting the schema and so on. So this is a little bit more of a compact way, but it does again have a bunch of dependencies that have to be installed. I found this blog, perfectlyrandom.org, handling Avro files in Python, which talks about all three of these cases and what are the pros and cons of each. Okay, Parquet files are very important. They are used significantly for data storage for analytic purposes. They are kind of the preferred storage format in the Hadoop ecosystem. And this is because the files are splittable and because they are stored in binary format with the schema attached to each block of data. It's a column store format, and each block of data or chunk of data has, as I said, the metadata written with it. Each chunk uses internal compression, so the files are already compressed inside, and they are used again for storage and analytical processing. There are two useful Python libraries that we can work with, PyArrow and FastParquet. PyArrow is the pure Python implementation, FastParquet is the C++ implementation. So to use PyArrow, we're just going to import PyArrow, we're going to import pandas, and we can basically grab any Parquet file. Here I used a URL, this is the taxi trip data as a Parquet file, and you can specify the engine option here. So here we're using PyArrow to load in that Parquet file from the URL, and that will put us directly into our data frame. You can swap out the PyArrow engine for FastParquet if you want a faster implementation of it. Now, the prior two examples read in the entire Parquet file. And sometimes if we have a very large Parquet file, which can grow to dozens of gigabytes, we may not be able to fit that into memory. Another technique that often is used or necessary is to read a Parquet file in chunks, that is to read only a certain number of rows. To do that, we can actually import this Parquet file from the PyArrow Parquet module. We can set a number of rows to read, and then we can grab a pointer to the file, that's pf, and then we can grab a subset of the rows. And that happens by calling the iterBatches function with batch size set to the number of rows you want to read. So again, if we're just doing some exploratory data analysis and we only want to get a small sample of the records, we can use this technique. The only limitation to this is that if you read in chunks like this, you have to read it from a local file. You cannot read it from a URL. So this file has to be locally stored on your file system. And again, once we're done from batches, we can grab that row subset and convert it to pandas. Okay, I think we're almost to the end here. Org files are called optimized row columnar format. Here's the specification, org.apache.org. Org files are the storage format for the Hive database. So Hive is a big data Hadoop-based analytical database management system. It runs on top of the Hadoop file system, and org files are their native storage format. It's a binary format with the schema, including the metadata for data types are written for every block and every chunk of data. Again, they use internal compression, and again, their use case is for storage and analytical processing. Org files and Parquet files are sort of similar in their approach, and they're used probably fairly equally for analytic purposes. For reading org files, again, pandas already have the read org function built in. We do have to import from PyArrow the ORC file support. Because ORC files are column-oriented, we can read in only specific columns. And again, this is super helpful for analytical processing. If we just want to read in the entire ORC file, you just give it the file name, and it turns it into a pandas data frame. Okay, there are literally hundreds of other file types. We've only touched on what are some of the most popular and important file types in data engineering, analytics, and data science, but you will come across other file types from time to time. For example, Excel files are very, very popular. Hierarchical data format, data frame storage using Arrow in the Feather format. If you have colleagues or group members who are working in the R programming language, their data might be stored in RData or RDA file format. So we might need to be able to read and interpret those files. SAS is a very popular statistics software, and they have their own format, SAF7BDAT. It's a binary file format for SAS data files. SPSS and Stata are also very popular statistics software. They have, of course, their own data file formats. And then the last two are not necessarily file formats, but they're ways of storing files. A tar file, which is called tape archive, is basically one file name that contains many files bundled up together. And last but not least, a zip file is a compressed archive that can contain many files. So sometimes if we get a tar file or a zip file, we need to decompress or extract all of the files that are inside of those archives before we can start to work with them. Last but not least, here's a little comparison table. And again, this comes from this blog by Aida NGOM. It's a comparison of different file formats. I've just kind of touched it up a little bit. I did remove a couple of columns because it kind of got confusing. But you can sort of see on this example here what the data type is, if the data types are stored within the file, how the schema is enforced or not, what orientation of storage it uses, either row or column, whether or not the file is splittable, compressed, whether it's useful for batch and or streaming, and whether the data is strongly typed or not, and finally, what ecosystems you might come across that are making use of these. So it's kind of a handy comparison chart. What do we use that for? There are many different file formats in use today. There are all kinds of trade-offs between file complexity, file size, and different use cases. If you are a software engineer, you're interested in understanding what file format is most appropriate for the application you're building. You might be thinking about what downstream use cases should you be considering. So if you have created an app or a web application, or you have an Internet of Things device that you're designing, what are the intended uses for the data once they get downstream? And that can guide your choice of data type. For data engineers, we're going to be the recipients of that data from the software engineers. And so what file format is the most appropriate for the use case, and how can you efficiently manage your data files? One of the things to keep in mind as a data engineer is that you really don't want to have to keep reinventing the wheel when it comes to data types. And this is a big issue with CSV files, because every time you read a CSV file, you have to figure out what the data types are. And so this kind of leads us a little bit more to using things like Parquet or ORC files. For a data analyst or a data scientist, you're basically concerned with what format is my data, right? Is it in a Parquet file? Is it in an XML file? And then how can I efficiently read and process that data? And again, we really like to not have to waste a lot of time figuring out column names, figuring out data types, and doing all of that kind of housekeeping. We'd like to see that work done earlier on in the data pipeline, maybe by the data engineer. All right, that's it. That's all I have to talk about for file types for today. Thanks for watching, and I will see you in the next video.